for seeing some results about dimensions of irreducible affine varieties in the last video. Now I wanted to have one video which explains about the dimension theory of reducible spaces, in particular reducible affine varieties. So in that setting, some results are not as nice as the results for irreducible spaces, but still it can happen in practice that you encounter a reducible space and then you still need to be able to work with it. So as an example, here you have the space X inside A3, which is cut out by the equations X1 times X3 and X2 times X3. So everything should add that. This happens in A3. And while staring at this ideal a bit, you can see it's the product of the ideal generated by X3 with the ideal generated by X1 and X2. And so this tells you by the rules of how the vanishing sets behave that X is actually union of this vanishing locus and this vanishing locus. Now, if you think about it for a second, well, the locus where X1 and X2 vanish, this is the locus of point 0, 0, and some X3. So this is the X3 axis, Y. And the locus where X3 vanishes, well, this is the X3 plane, where X3 is 0, and then the other two coordinates are allowed to vary. And clearly these two meet in a single point in the origin. And for example, we have then seen that this is a connected space, at least, but it is reducible because it's written as this union of two irreducible subvarieties. And then you can ask, what about the dimension of X? In particular, given that, well, it's easy to see here that this Y, if you compute, for example, the cruel dimension of the quotient, then you see this cruel dimension will be one-dimensional, which fits to the fact that it's just a kind of line. And the dimension of this here will be 2. As follows, for example, from the fact that this is cut out in the ambient 3-dimensional space by a non-zero equation. So by this result derived from Krull's principal ideal theorem, it has dimension 1 less than 3, so it has dimension 2. So X is composed as a union of a 1-dimensional space and a 2-dimensional space. And then you ask, like, what is the dimension? What is the codimension of different things in there? And so, for example, if you start with a single point on Y away from the origin, and we call this set Y0, then we can ask, what are the chains of irreducible subvarieties containing this? And well, you can, of course, take the full subvariety Y. This contains this, but then here it stops. You can't go any bigger and still stay irreducible. I mean, because when you would try to take any part of this plane, you would start getting something which is reducible. And then you have a bit more luck if you start with a point on this 2-dimensional plane, Z0, then you can take, for example, a line going through this point. This is irreducible. This gives you Z1. And then Z1 is contained in the entire plane Z2. So here you have a chain of irreducible things of length 2. So these pictures above, you can make this precise, but the pictures above show actually two maximal chains of irreducible subsets starting in either Y0 or Y1. And then it is true that the codimension of Y0 is indeed 1. You can only go one step. The codimension of Z0 is 2. You can go 2 steps. And so we see, in contrast to the result last time, that when the variety X is irreducible, its dimension is also the codimension of any point in it. Here we see that different points in the variety can have different codimensions. And that codimension of a point can then be seen as a kind of local dimension of X at Y0 or Z0. And that also fits with our intuitions with degrees of freedom, like in a neighborhood of this point Y0, you basically have 1 degree of freedom, whereas here in the neighborhood, you should have 2 degrees of freedom. Okay, and so our guess now maybe, what is the dimension of this entire space? Well, it's the biggest length of chains of any irreducible subsets. So we certainly see from this chain that the dimension is at least 2. And then you can check indeed, and we're going to do that in a second, that this gives you the dimension of x. So dimension in this case is 2. And to make this precise, we start with kind of 2 exercises, which also give nice sanity checks for this notion of dimension. Namely, if X is a topological space and A is a subset, well, it also carries the relative topology. And then the claim is the dimension of the subset is less or equal dimension of X. Certainly, it shouldn't happen that you go to a subset and suddenly the dimension is bigger than the ambient thing. That would be very counterintuitive. And then the second exercise is that when X is a Noetherian space and Y is an irreducible subset, then the claim is there exists an irreducible component of X containing Y. So X being Noetherian means we have an irreducible decomposition. And then the claim is if you start with something irreducible, it will fit in one of the parts of this irreducible decomposition. Okay. And we're going to use these exercises in the following proposition. So the proposition tells you if you have a reducible space, like a reducible Noetherian topological space in this case, and you have its irreducible decomposition like this, then the dimension of X is the maximum of the dimensions of its irreducible components. And then applying this here, see the irreducible components have dimensions 1 and 2. And so the full space has the maximum of these 2 numbers. And so this is 2. And the second thing is that you can also, you still have some statement about dimension of X being able to be expressed in terms of codimensions of 1-point sets, namely dimension of X is a supremum of all these codimensions when A runs through all of X. And the proof is not so terrible. So for the first part, that this is the maximum of the dimensions, let's first show this inequality. So, well, any of the xi is, of course, a subset of X. And then by the exercise, its dimension is less or equal dimension of X. But so in particular, all of these numbers here are lower bounds for this. And then also their maximum is still a lower bound. And that one was very easy with the exercise. And then the other direction, here we have to be a bit careful. So bear with me for a second, because we want to basically, we want to formulate a proof which works even if the dimension of X happens to be infinite. And then we need to be a bit careful. So let's say the dimension of X was at least n for some n. Then this was the supremum of all chains of irreducible subsets. So we certainly find a chain like this of length n. And then, well, this chain ends in yn, and this is then contained in X. But by the second exercise here, this yn is contained in one of the irreducible components of the space X. And so instead of terminating this chain in X, we could also terminate it in xi. Would still be correct. But then this is a chain of irreducible subsets of xi. And so the dimension of xi is at least n. And then, well, the dimension of X was defined as the maximum or the supremum, would maybe be more correct here, the supremum over all n, such that the dimension of X is at least n. And then this is smaller or equal to the supremum over all of these numbers dim of xi. And so that proves the first part. And I think you will find that the proof gets kind of easier if you can assume that X is is finite dimensional, because then you can just say, well, if the dimension is n, then we find such a chain, and then we find an xi which has dimension also at least n, and this gives you the other inequality directly. And then for part D, I give this as an exercise because the proof is very, very similar. It's kind of just exactly the same ideas, and you can see it as an exercise. And I mean, if you don't want to do the exercise, you can also look at Gutmann's notes, because this is explained in this remark here. Okay, so we can control, even if X is a reducible space, we have different ways of computing its dimension like this. And in particular, the part A of the proposition reduces it to finding the dimension of irreducible varieties, and then we're again in business and can use commutative algebra. So then I want to conclude with some definitions and a nice example. So we started the video with this example of a space which has different components of different dimensions. And these are nice for illustrating these concepts of local dimension and so on. But often it is possible to prove stronger results for spaces where all the irreducible components have the same dimension. And so we want to give this concept a name. And these are the pure dimensional spaces. So we say in a Euclidean topological space, X is of pure dimension n. Sometimes this is also called of equidimension n. If every irreducible component of X has dimension exactly n. And then with this definition, we can now define concepts which are really central and important in algebraic geometry. And then we can already define them now for affine varieties. Namely, such a variety is called a curve if it is of pure dimension 1. It's called a surface if it's of pure dimension 2. And then these were kind of names for specific dimensions, but also you can give a name for something of a specific codimension. Namely, you can say this affine variety is a hypersurface in a pure dimensional affine variety Y if, well, it's a subvariety and it is of pure dimension one less than the ambient variety. So hypersurface means it's not necessarily surface, but it means it is a variety of pure dimension exactly one less than the ambient dimension. And so I want to illustrate this with a kind of very fancy example, also giving a bit of a foreshadowing of what comes later, because that example will reappear. And so the basic example is that we cut out inside A3, three-dimensional affine space, we cut out affine variety S by a single equation. And the kind of equation that we want, so we have three-dimensional space, so we have three variables, x1, x2, and x3. And the equation that we want is basically an arbitrary equation of degree 3. And this is called a cubic. And so the entire variety will be called a cubic surface. And you can think about it for a second, and then you can see that to specify an arbitrary such equation, which is cubic in 3 variables, you need to specify parameters A, B, C, and so on of the different terms in this equation until t. So, and it turns out if you count, this is exactly 20 parameters. And so, for example, if you choose A to be 1 and B to be 1 and the other parameters to be 0, then you would simply get an equation of the form 1 times x1 to the 3 plus 1 times x1 squared x2 is equal to 0. But in general, you could place arbitrary numbers here. And then for each choice of these parameters, you would get one equation and therefore one affine variety. And then the claim is that unless you choose very specific numbers, namely all of these numbers to be 0, then as or at least the kind of first numbers. So here you see it's an equation of degree at most 3. So in particular, you have some linear terms and then a constant term. And if you choose all of the terms having some variable to be 0, then it's just a vanishing set of this constant, and that would be either the full space if the constant is 0, or it would be the empty space if the constant is non-zero. These are very boring cases. So if you exclude those at least, then you do get with S a non-empty hypersurface and a surface. So that is kind of the example that we have here, because then inside the three-dimensional space cut out by a single equation by the Crow's principal ideal domain, all of the irreducible components of this will have dimension 1 less, and so it's equidimensional or pure dimensional of dimension 2. So this is surface. And also because the ambient space is 3-dimensional, it's 2-dimensional, it's also a hypersurface. The codimension is equal to 1. So this is a very fancy example, and of course this is not very dependent yet on us having chosen exactly a cubic equation. But then the kind of cool fact is that for most values of these parameters here, and I'm going to say in a second what I mean by most, but it is true that for most of the values of the parameters which you can choose, you get this surface S. And then I claim that there are exactly 27 lines of inside A3 which are contained in S. So line in this three-dimensional space is simply obtained by taking a one-dimensional vector space to the origin, and then translating it maybe by some vector in k to the 3. This gives you a line like this. And the claim is, among all of these possible lines, most lines will not lie in the surface, and then there's just a finite number, 27 of them, contained in there. And then, in particular, so here's a kind of illustration of this. You have the surface, and then you see the 27 lines. And then if you take, for example, the union of these 27 lines, then this will be indeed a reducible curve. So it will be pure dimension 1 and therefore satisfy the definition of a curve. This was a very fancy way of giving an example of a surface and a curve. But that's the kind of cool result that you can show in algebraic geometry, but this needs a lot more techniques. And one of the later chapters of Gatman's script discusses this. And I think we're going to see the ideas behind this. And the final thing that I should say, and that's also kind of a foreshadowing of something which will later be important, is I claimed here something like for most values of these parameters, the following statement is true, that you have exactly 27 lines and so on. And what do I mean by most here? So one sense in which you can interpret this is that, for example, if you work over the complex numbers k equals to c, then you could say, well, these are all complex numbers, and then you could do something like choose a small ball around the origin in the complex numbers, and then basically draw every one of those at random from this ball. This makes sense with respect to the Lebesgue measure, and this would be what you could call kind of a random choice of parameters. And then this statement is true that somehow with probability 1, this would be a correct statement. But in fact, there's also a way in which this kind of most makes sense for arbitrary base fields k. And so this is the following. This is written here. So it is saying that if you look at the set of all such tuples of parameters, this you can see as an element of A20. So it means for every point in this space here, you get a single hypersurface like this. And the claim is the set of all such things which have the property of having exactly 27 lines, is a non-empty set, and it is Zariski open. So we have seen all the words here. So somehow it's non-empty, so it means it holds for at least one choice. And then it's also Zariski open. And we have gotten the intuition that Zariski open sets are actually really big inside here. So we have seen, for example, that any two of them have non-trivial intersection. We have seen that in the Zariski topology, they're dense in here. And so this gives you an idea that indeed the set of all such parameters which have the nice property is a really big set. Conversely, you can kind of reformulate this and say the set of these parameters where this property fails, where something goes wrong, is Zariski closed and not all of A20. So it means this set is cut out by some non-trivial system of equations in these parameters. In other words, if you want to check whether something goes wrong, then your parameters must satisfy a non-trivial system of polynomial equations. And so again, you would expect if you choose them kind of randomly, then they would probably not satisfy this system. Okay, so that was a bit of an fancy example with a bit of an outlook. If this was kind of too fast or a bit too confusing or too many, this equation is very long and so on. So if it was too confusing, don't worry so much about it. It's only kind of meant as looking forward to something which we're going to see later after a lot more preparation.